Hello there and welcome back. In this episode, I want to talk to you about or want to show you how you can probe on your MCU or your dev board to confirm the frequency at which the SYSCLK is running. I know we have already done this in code and we basically stored it in a variable, so during debugging we saw it, right? But there is another way, and that is what I want to show you. And just so I keep this video not so long, I have gone ahead to write the code already, and I'm going to go through with you so that you will understand every line. Okay, so everything in system clock config is what we did in the previous episode, so it needs no explanation. Nothing new has been added here. What I have done is I've created a function called route SYSCLK to MCO. Now I'm going to explain to you what this MCO means. MCO basically means Microcontroller Clock Output, and it is a signal that is already in your MCU. So in the wiring of your MCU, they have made it such that there is a connection from SYSCLK to one of the IO pins, and if you configure things properly, you can probe that particular pin to check some of the properties of the clock signal. I mean, if you read it like we did previously, you can obviously see the frequency, right? But what if you need other properties of the signal, like the rise time, the falling time, or you want to check if it's even a proper square wave and whatnot, right? So there is MCO, and that stands for Microcontroller Clock Output. In my particular microcontroller, the STM32 F303, which is on the discovery board, the MCO is routed to pin PA8. And how do I know that? So let me just open the data sheet here. And first of all, I know you know about the GPIOs, right? And we have learned how to control them. What we haven't discussed so far is the fact that they are not just for general purpose input and output. They also serve alternative functions. For example, all the peripherals on your microcontroller, like UART, ADC, DAC, the timers and whatnot, all these peripherals have to communicate with the outside world, and the way they do it should be through some pins, right? In your ST MCUs, there aren't dedicated pins for these peripherals. They pick them out of the general purpose input output pins. So that is also why when you are writing code to control it, you have to specify the mode in which you are operating, and one of the modes is alternative function. So it just happens that when you come to the data sheet, and I mean, to make it simpler, I can actually just search for alternative function. And okay, it says alternative functions for port A. I know because I have read already, right? So if I click here, this is a table of alternative functions. Each alternative function is identified by this identifier here, AF0 to AF15 for each port, and then the alternative function is available on some specific pins. So if you look at AF0, for example, it means you can configure PA1 to function as AF0 for this particular case, or PA8 to function as AF0, which will become MCO. The MCO here stands for Microcontroller Clock Output, like I've said quite a number of times in this video. So we are going to configure PA8 in code to enable the clock signal to be available on it, so that we can probe PA8 and see the system clock frequency and other properties, right? So that is what this function is doing, route system clock to MCO. Now if we go to the function definition, It's very simple and it's very familiar. So what I'm doing is I'm enabling clock access to GPIOA, and remember, you can only call this function after you have done your system clock configs. If you call it before, what you will see wouldn't be what you did. It wouldn't match what you did in the system clock config function. So you need to configure your system clock because you want to probe it, right? So you need to configure before you do the probing. So here I'm enabling clock access to GPIO port A because we are targeting port A pin 8. All right, and then this is the familiar code. So I create a GPIO init type def, and I set the pin to GPIO pin 8 because that's our target. And look at the mode. Previously, I'm sure you have seen GPIO mode output PP input. This is GPIO mode AF. AF stands for alternative function, PP push pull, right? So you say the mode is, we are basically configuring this pin to be an alternative function, and then we have to specify the alternative function that we want it to serve. So you say cfg.alternate is equal to GPIO AFO MCO, and the way we know that is because we have checked this table in the data sheet. So this is not in the reference manual. I'm looking at the data sheet now. Okay, so I know from the data sheet alternative functions for port A that if I want MCO, I need to configure PA8, all right, as AF0. So let's look at the code. You can see that here I said GPIO AF0 MCO, so it matches what we saw in the data sheet. I'm configuring the GPIO pull, no pull. I don't want it pulled up, neither do I want it pulled down, right? And then the speed, this is very important. The GPIO pins can function at different speeds. Now, because we are probing the system clock, which could be very fast, you know, from 8 megahertz, and if we do PLL, we can clock it all the way up to 180 megahertz on some boards. So you want to set the speed to the highest frequency. Otherwise, when you probe, what you see is going to be different. So let's see what are the alternatives here. So if I do this, you know, there is GPIO speed, frequency high, low, and the medium. So I chose the highest. And then we call the familiar function HAL GPIO init. We pass GPIO port A and then the init type def. And the last call that we have to do is here. This is HAL RCC MCO config. And then you pass it this constant RCC MCO1. It is called MCO. On my particular board, there is MCO1. On other boards, you can see MCO1 and MCO2. What it basically means is that the same signal is routed to multiple pins. So you just choose where you want to route it, right? But in my case, it's just MCO1. So I just say HAL RCC MCO config and MCO1. Let's look at the function signature. Maybe it will help us understand. So you basically tell it the MCO is the source and a div. This is a prescaler if you want to prescale the output before you probe it. So in my case, I have said the source is RCC MCO source SYSCLK. So I am connecting SYSCLK to this pin, and I am not using any prescaler here. So RCC MCO div 1 basically means I'm not dividing, so I'm not prescaling it to anything. So if it is 8 megahertz, I expect to see 8 megahertz on my board, right? So now let's go to my scope view, and this is what you see. I have connected it to my probe. I can show you how I did the connection. So I'm using a Digilent analog discovery 3 here. So if I zoom in, you'll see that this is PA8, and I've connected one of the cables beneath the board to PA8 and one of the cables to ground. So I'm just probing the signal between PA8 and the ground, right? I have another photo that I took from the other side, so you can see. So this is underneath it. It's just one part connecting to ground, another part connecting to the PA8, and then it comes to the Digilent analog discovery 3. So the software we use to view what the scope is doing is called waveforms, and that is what you are seeing on your screen right now. Now you might be surprised, like, okay, you are expecting a perfect square wave, but what we are seeing here is nothing close to, I mean, it looks like, but it is not really a perfect square wave, and there are many reasons for this. One, the MCO signal is not meant to be used as a source for another microcontroller. It is just for debugging purposes. Okay. 2, the speed at which the GPIO ports can operate actually places a limitation on the quality of the square wave that you can measure. 8 megahertz is quite high, and even above that is more higher, and the GPIOs are not the best pins to be used for generating of square waves and stuff. They have inherent limitations electrically, and that is one of the reasons why we are seeing this. Another one could be the quality or the attenuation level of the probe that is being used, and even the routing on the PCB itself could contribute some capacitances that is going to adversely affect what we see. But the most important thing here is that we can actually look at it, and then we see that, okay, indeed there is a clock coming in. So there is a clock coming in on the board. Now I have pressed the reset pin, so you can see that the clock is gone, right? If I release, then the system clock config executes, and then the MCO is activated, and now we can probe it on PA8. Now, how do we confirm that this thing is actually an 8 megahertz signal? I can go to measurement, I click on add defined measurements. I'm interested in frequency, so it's a horizontal measurement. I click frequency and I click on add. So here you can see that it's 8 megahertz and sometimes 7.9 megahertz, but it's actually 8 megahertz, just as we configured in the code. So anytime you have reasons to think that your system clock is misbehaving, or the configurations that you did in code is not behaving as expected, apart from reading like we did in the previous video and showing it, you can also probe it with a scope or a logic analyzer, anything that basically helps you to visualize voltage changes with respect to time. So that is it, ladies and gentlemen. Thank you very much for watching this, and I will see you in the next video.